Good morning. In the last class, we have learnt about the Thevenin's theorem applicable to networks, and we have replaced Thevenin's equivalent network across the terminals or across the load with its equivalent circuit, and we could able to find out the corresponding voltage across the load or current through the load. So today we'll take up a different problem which is having a controlled sources in the network. See, in this particular example, we have a controlled source here. So what type of different voltage controlled sources are available? So voltage controlled voltage source, current controlled voltage source, current controlled current source, voltage controlled current source. In this example, it is the current controlled voltage source. So let us start solving the problem with the first step of we have learnt in the previous session. So what we have to do, we need to remove the load and find out the Thevenin's voltage across the terminals A and B. A simple mesh equation in the first loop will get us the result of the current IS. What is the value of the IS? So that is 86 minus 86 plus 80S, that is with the two resistors, plus 6S, which results in IS is equal to 1 ampere. Applying the KVL for this loop will gives us the Thevenin's voltage across A and B as 36 volts. So now next step is to find out the RTH. So we continue with the similar step which we learned in the previous class. So which is removing all the independent sources, but we should make sure that we retain the controlled source. We should not remove the controlled source. But to find the RTH, a simple series parallel combination of resistors reduction is not possible. So for that, what we need to do is we need to find out the short current with a different approach. So let us excite the circuit with a simple 1 ampere current source at the terminal A and B. So once we apply that, so we could able to find out the value of the IS, so which is minus 15 by 43, and then we can find out the RTH by applying the KVL to the outer loop. See, the resultant voltage is 57.4 volts, and the voltage current through the terminal A and B is 1 ampere, so which results in the Thevenin's resistance as 57.4 ohm. So now we can replace the Thevenin's equivalent circuit across A and B with Thevenin's voltage and in series with the Thevenin's equivalent resistance across the terminals A and B, that is the load 100 ohm. So once we replace the network, so we can easily find out what is the voltage across 100 ohm, which is 22.9 volts. Let us take up one more example where we need to find out the voltage across where we need to find out the Thevenin's equivalent network across X and Y. So first, to find the RTH, excite the terminals X and Y with 1 ampere current source. Then with the simple mesh analysis, we can find out that Ix value is 0.5 ampere. The mesh equation we can write with the inner loop. Then we can find out the voltage across the terminals X and Y. Once we find out the voltage across terminal X and Y, we can find out the Thevenin's resistance. It is 50 ohm resistance. Here, one more thing what we need to do is we need to observe the network which we considered across terminals X and Y is not having any independent voltage sources. So Thevenin's will be 0 volt or a short circuit. It's a very simple conclusion that we can come up. So once we find out RTH, it is the completion of the problem. So we can replace VTH 0 volts and RTH 50 ohm, and the remaining, this right half of the part is with the 100 volt source and 50 ohm. So we can find out the VXY voltage, which is equal to 50 volts with a simple voltage divider formula. Thank you.